So just to remind you and me, here is the definite integral that I am trying to approximate using Riemann sums. We just found the lower Riemann sum, so now we're going to find the upper Riemann sum using circumscribed rectangles. I'm going to stick with my 3 equal increments, but instead of finding the x value that gives me the lowest f of x, I'm going to find the x value that gives me the highest or the greatest f of x value for each of these increments. So for my first increment, my x value over here gives me the highest f of x value, so that's going to be the height of my first increment. Over here, this value of x gives me the greatest f of x value for this increment, so that's the height of that rectangle. And my third increment over here has a high point over here, so that would be my sample point. So now I have my 3 circumscribed rectangles. The area of these 3 circumscribed rectangles, the sum of those areas, will give me my upper Riemann sum. So some cool things to think about. My lower Riemann sum is actually my lower bound for the actual definite integral for any function, really. And my upper Riemann sum is the upper bound. This leads us to the definition of the definite integral. If the limit of my lower Riemann sum as delta x approaches 0, so each of my rectangles becomes really skinny, if that limit equals my upper Riemann sum limit as delta x approaches 0, so when those rectangles get really skinny, if these two limits are equal to each other, then my definite integral from a to b of my function with respect to x is called integrable from a to b. Not only does this function have a definite integral from a to b, but that definite integral is actually equal to the limit of the lower Riemann sum and the upper Riemann sum as the width of those rectangles approaches 0.